Welcome students to your favorite channel PSC producer classes, and today's actually we are going to start with this is day 4, and this is day 4, the numerical king series. So for that particular days we are starting electrostatics, that is question number 25 to question number 30. In the previous class, you see that I have completed about for the first day it is will be 1 to 50 numericals, and then for the second that is 20. So all the numericals, that is from question number 1 to 20, is completed, and for that particular days I completed question number 25 to question number 30. So let's start. And first of all, I want to say that mainly for the aspirants of that is NEET or IIT and aspirants, basically those who have not completed their concepts about resolution of vectors, Coulomb's law, friction, free body diagram, spring force, and concepts of equilibrium of charges. And for that particular numericals, it is very important to clear 25 to 30, because 25 to 30 all the numericals are cover these 6 type of complications, 6 type of concepts. So we actually for the NEET and joint, we always try to complete a numericals that consist of or clear more and more concepts. So first of all, choose that type of numericals that will help you. So first of all, I want to say or complete a little bit amount of these concepts. First of all, if we take the resolution of vectors. So what is resolution of vectors? Suppose a boy standing here like that, so there is a mg, that is weight, acts in the downward direction, and there is a reaction force due to these surfaces is r, that is the boy is in static equilibrium. So there is no component of force. These two type of forces are act. But if I suppose like that, if I stand here like that, then mg acts downward and the reaction force acts in the upward directions. But if I try for tilt myself like that, if we try to tilt myself like that, suppose this one is the figure, so this is like that, tilt one, then you also try it, then realization is more better. So if I tilt like that, then we press the fingers on the ground, so the ground gives a reaction force along this particular direction, so gives a reaction force. This is reaction force, but the mg is always along the downward direction, that is mg. So for the equilibrium, if I want to be in equilibrium with that pose, then reaction force resolutes like that. If this is angle theta, then this angle is also theta, because it is so simple, this is vertically opposite angle. And so r cos theta acts in the upward direction, and r sin theta acts along this direction. Then what is the function of these particular components, r sin theta? It gives a force, that is r sin theta. R sin theta is trying to tilt that particular body in particular directions and a force capital F that is acts to equilibrium the these components are sin theta. So when you tilt yourself, that it required a backward force, and that particular force or cos theta can equilibrium the weight. So this is the resolution of vectors. This is the resolution of vectors. And if we go for the next, that is second concepts, that is Coulomb's law. So from Coulomb's law, you know that F equal to kappa Q1 Q2 by R square. So this is a proportionality constant, Coulomb's proportionality constant, and it depends upon the system of units used. And in SI system, this is Q1 Q2 by R square. And most of the numericals to be done in that particular book, says Verma, is in SI units. So kappa equal to 9 into 10 to the 9 into Q1 Q2 by R square, and this is Coulomb's law. This is F is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So F equal to 9 into 10 to the 9 Q1 Q2 by R square. And the next one is friction. Friction is basically a retarding force. When a body, we applied a force in a particular direction, then reaction, and then the friction acts in the opposite direction. And if the mass of this body is m, then weight mg acts in the downward direction, and the reaction force acts in the, that is normal reaction. This is called normal reaction. So this is what is this. And if a P is the force applied on that particular body, then friction force comes into play. And this frictional force is equal to mu into normal reaction, mu into capital N, that is normal reaction. So here N equal to mg. So here mu into mg. But for that particular concept, free body diagram, if the force, if this is a particular body kept on the inclined plane, then mg acts along this direction. Mg acts along this direction. If we resolute the vectors, that is, if this is theta, then along these directions mg cos theta. And you have to remind that always if theta is the angle, then R resolutes itself. It is actually a function, trigonometrical function, and the reaction force is along these directions. It will be cos theta, R cos theta. So it is a division or resolutions vector depends upon the trigonometrical functions. So mg cos theta, always mg cos theta acts along this direction, and mg sin theta in this direction, mg sin theta. So normal reaction, here normal reaction equal to mg cos theta. Here normal reaction is mg cos theta, but here the normal reaction is mg. So normal reaction means weight. Isn't correct or not? This is exactly not, because mg, if the body is in that particular position, then n equal to mg, but if this is in slanting position, then n equal to mg cos theta. So free body diagram, it is basically NLM, Newton's laws of motion. It is a part of NLM. So free body diagram, concepts of free body diagram is important for that particular numericals. And the second, fifth one is spring force. What is spring force? A spring force is basically, if we suppose this is a spring, and a weight is given here, and this is a spring, and it is a surface, and this weight tries to compress the spring along this direction. Yes or no? Yes. this body compresses the spring along these directions, and hence there is a restoring force comes into play. And what is the amount of restoring force? And we all know that this restoring force Fr is proportional to the displacement, proportional to the displacement, and that is we have to take a negative sign, because when the spring compressed, the restoring force comes into play and tries to back the spring in its own position. So when it compresses a force, the restoring force acts along this direction. That is, we can write as F suffix R. So F suffix R is proportional to minus X. Is it clear or not? So F is proportional to X, or this force when we take the magnitude of this one, and this is equal to Kx. So simply here K is the force constant. So this concept is more vital for that particular numericals. That is question number 24. So we see that how many types of concepts are clear along this particular numericals, that is from 25 to 30. And the next one is the concepts of equilibrium of charges. What is equilibrium of charges? Suppose there is a charge Q1 and there is a charge 2Q1, or it may be Q and 2Q. So there is always exist a repulsion force amongst the two charges, because we know that from the fundamental law of electrostatics, we know that the like charge repel each other and unlike charge attract each other. So here there is a repulsion force among Q and 2Q, and if we want to equilibrium that particular charges, that is Q and 2Q, then we must have placed a negative charge along a particular positions, so that this particular charge can attract this one and this one, and all the systems is in equilibrium. Why? Because there is a repulsion force between these and this. So the repulsion force between Q and 2Q balances the attractional force between these and this one. So this is the particular concepts. I repeat again. If you want to solve the question number 25 to 30, then clear the concepts of resolution of vectors, Coulomb's law of friction, free body diagram, spring and constant, and the concepts of equilibrium of charges, and all the these are the all the concepts. Then let's start with the numericals. And so the 25 numericals 25, and let's start with 25 numericals. Question number 25. Question number 25. So let's read the questions. Two identical pith balls. So the question number 5 is question number 25. Sorry, 25. Question number 25. The two identical pith balls, and each carrying a charge small q. And if you want to write down the equations or question number, then I read and you can write it, or otherwise you can download it, that particular PDF. So two identical pith ball and each carrying a charge small q are suspended from a common point. This is we can write this one and this one. So what is pith ball? We assume that this is a very light ball, and this is a very light ball, and they are suspended from a point. They're suspended from a point, and this since this is a charge q and this is also charge q, so the Yes, this one is repel this one, and this particular charges repel this particular charge along this direction. So this is a Coulombian repulsion force. And what is Coulombian repulsion force? And there is the amount of forces acts between the two particular charges. It may be like or unlike charges. This is F equals to kappa q1 q2 by r square. So kappa is the Greek alphabet and it is 9 into 10 to the power 9. So the force is F equal to 9 into 10 to the power 9 into q means q square. So this is 9 and this is q, and divided by yes. And if we here if we take this distance like x, then there is a fraction x by 2. So we can take this distance as 2x. Why? Because this is the concepts and this is the way to solve the numericals easily. So this one is x, this one is x. Okay, and this is a length, particular length. So the question is two pith ball. The question is two pith ball are a small distance apart, and the angle between them is 2 theta. So this one is theta and this one is theta. And if the mass of this ball is m, then calculate the mass of the ball, isn't? Yes, two identical pith balls each carrying a charge q and suspended from a common point by two springs of equal length L. Find the mass of each ball if the angle between the string is 2 theta in equilibrium. So in equilibrium conditions, this charge is the repel with this charges with a particular force, and there is mg. So students, first of all you have to take into account all the forces acts on the particular, all the forces, that is Coulombian force acts, and this is weight, and also it is the concepts number 1, that is resolution. What is resolution? Here tension force within the string acts. So if tension force acts along these directions, then we can resolve it like that. So this is theta and this is also theta. This is, why this is theta? Because it is alternate angle, so simple. So theta, alternate angle, and this is t cos theta, and this is t sin theta, Yes or not? Yes. This is t sin theta. So this is t sin theta, and this is t cos theta, and this is mg, and this is Coulombian force. So there are 4 type of forces can act on that particular mass particles. 4 type of forces. T cos theta is basically a component of tension. T sin theta is also a component of tension. We can resolve the vectors because tension is a vector quantity. So T sin theta in equilibrium condition, we can write in equilibrium condition, in equilibrium condition, T sin theta equal to this one. This one is 9 into 10 to the power 9 q square by q1 q2 by this is 2x, so 2x square. So 2x square q1 q2 by distance square, and the t cos theta equal to here mg. So this is equation 1 and this is equation 2. T sin theta equal to this one and t cos theta equal to this one. So divide this equation 2 by 1, divide 2 divided 1. So sin theta by cos theta means tan theta. Tan theta equal to 9 into 10 to the power 9 into q square. So q square by 4x square by mg. Two divided 3. Tan theta equal to 9 into 10 to the power 9 into q square by 4x square mg. Is it clear? Yes. So you have to calculate the mass. So m equal to 9 so 9 into 10 to the power 9 into q square divided by tan theta 4x square into g. So m equal to 9 into 10 to the power 9 q square by tan theta into 4x square into g. But then in numericals, what is x? Isn't given or not? No, this is not given. So you have to take this one as sin theta. So sin theta equal to perpendicular by hypotenuse, that is L. So x equal to L sin theta. This is the formula. So if we take this one as x, then x by 2. So it's little bit critical. So x equal to this one. So this is equal to 9 into 10 to the 9 into q square by tan theta into 4 into x square. X square means L square sin square theta 4x square into g. So this is the answer, mass. And most of the books takes in a different form. If we 9 into 10 to the power 9, so 9 into 10 to the power means 1 by 4 pi epsilon naught. So if we apply 1 by 4 pi epsilon naught, then the results takes the form 1 by 4 pi epsilon naught. So 16 4 pi epsilon naught in place of this one. If we place 4 pi epsilon naught, then 16 pi epsilon naught 4 pi into 4, 16 pi epsilon naught, or tan theta as cot theta. 1 by tan theta means cot theta. It is meaningless. So 16 pi epsilon naught into L square sin square theta into g. So this is the answer of the book. So this one is this. So m equal to this. So this is numericals, and most actually these numericals can clear your concepts a greater view. So you have to clear all the concepts. That is concepts, all the 6 concepts are frequently used in question number, from question number 25 to question number 30. So the first question is completed, question number 15, and the next one is question number 26. So I erase the numerical king series day 4. And I repeat again, if the answer is like a different, then say wow, what a concept, and subscribe my channel. So question number 26. A particle having a charge 2.0 into 10 to the power minus 4 coulomb. Yes, a particle having a charge 2.0 into 10 to the minus 4 coulomb is placed directly below and at a separation of 10 centimeter from the bob of a simple pendulum at rest. So you have to draw a simple pendulum. So this is the pendulum, and this is the bob, and a charge is kept. Where it is kept? A particle having a charge this coulomb is placed directly below and at a separation of 10 cm from the bob of a simple pendulum at rest. So there is a charge. A particle having a charge, and this charge is 2.0 into 10 to the power minus 4 coulomb. Is placed directly below the separation of 10 cm. The separation between the two charges is 10 cm. From the bob at rest, the mass of the bob is 100 gram. So the mass of the bob M equal to 100 gram. M equal to 100 gram. The mass of the bob is 100 gram. What charge should be the bob be given so that the string becomes loose? And you have to calculate the value of the charge that is given on the bob so that the string will loosen. So why the spring is loosened? Because due to the it is so easy, because due to the when these charge particle repel this one, then the spring is loosened. So it is a basic problem. So you have to calculate what are the different forces act on that particular bob. That is, the first one is mg, because it is hanging from particular point. So mg acts downward directions, and if these charges repel this one with a force, Coulombian repulsion force, then what is the amount of this force? F equal to 1 by 4 pi epsilon naught, that is 9 into 10 to the power 9 into Q is the charge of the bob, and 2.0 into 10 to the power minus 4 coulomb. So kappa into Q1 Q2 by R square. Here R is given in a different unit, that is 10 centimeters. So 10 divided by 100, and this is square. Isn't okay or not? Yes. 9 into 10 to the power 9, that is proportionally constant, and Q is the charge of this one, and this one is the charge of another body, divided by the distance of separation is 10 centimeters, so 10 divided by 100, this is a square. Yes, this is okay. So this is we can simplify it, and this is 9, and this is like a similar, but it is Q. So 9 into 2, 9 to the 18 into 10 to the power of 5. 9 to the 18 into 9 minus 4. So 5 divided by 10, 0, 0 cancel, and then 100. 1 by 10 square means 100. So this is 10 to the power 2. So the force is 18 into 10 to the power 7 Newton. And this is the repulsion force, and the weight is mg. So the weight equal to mg, or m means 100 gram. So this is the CGS unit, so you have to divide it with 1000 into g. What is the value of g? You have want to take 10. Yes, 10, or you can take 9.8. It is better to take as 9.8 or 10. 9.8 is the average value of this one. So this cancel. Yes, 1 Newton. Yes, this one is here it is Q. So Q. Sorry, Q. So this weight is equal to the weight, this weight is equal to the repulsion force, Coulombian repulsion force. So weight equal to repulsion force. So 1 Newton is equal to this Newton, that is 18 into 10 to the power 7 Q. So this is the Q equal to 1 by 18 into 10 to the plus 7. So this is Coulomb, or 1 by 18 means approximate 5 90 90 10 100. So 5 approximate 5.2 something, 5 into 10 to the power 0.05 sorry, 1800 point 1 0, then 1 10.0 sorry, so 0.05 into 10 to the power minus 7. So if we take this as 5, then 10 to the power minus 9. So this is the question number point. Yes, it is 5 into 10 to the 9 coulomb. So approximate nanocoulomb order. Is it clear or not? 26. Yes, 26 is cleared, and then I think it is clear. Then 27. Two particles A and B having charges Q and 2Q respectively are placed on a smooth table with a separation of D. If the answer, what is the answer? What is the answer? So question number, yes, 5.4, approximate 5.4. If you take this value as 9.8, then 5.4 into 10 to the minus 9 coulomb, is it? Okay. The next one is 27. So 27, question number 27. And what is the question number 27? Two particles A and B having charges Q and 2Q. So two charged particles Q and 2Q are given at a particular distance of separation, smooth table on a distance D. So D is the separation distance between these and this one. Yes, it is clear or not? There are two charges, and one charges is double the another. The respectively, and a third particle C is to be clamped on the table. Why it is clamped? Oh yes, because these and these one repel each other. And if we clamped a particular charge, suppose clamped a particular charge, capital Q, clamped a capital Q charge, clamped one, this means you have to bound that particular charge. If not bound, then this charge and this charge, repulsion takes place, and this charge and this one is also repel each other. So there is no equilibrium, and this is another way. And if we place a charge of minus Q here, then this charge and this charge, attraction takes place, and these also attract this one. So attraction takes place, and there is a repulsion force between this and this one. So repulsion force between this one is attraction of this one. It takes that particular three charges in an equilibrium position. Yes, but minus Q charge, when you place that minus Q charge in a particular position, that is, it is very close to the 2Q or very close to the Q. If we place this one very close to 2Q, the distance is less and this distance is also greater, and these particular charges is less amount of this one, so it is not possible. So if we change the distance, capital Q is and this is minus Q, so the distance is small, but this is distance is greater, but the charge is very large. Oh yes, it is possible. So if we take this is x distance from this one, then this distance is d minus x, isn't? Yes. So question is, two charges q and 2q are separated by a distance d, and where a third charge be placed or clamped so that the three charges are in equilibrium position. So what is equilibrium? Means the net force is 0. What is equilibrium? The net force is 0. So the force between this and this one is Coulombian force, so kappa into Q, and if we take the magnitude, so you can just write as plus Q. So QQ by x square is equal to the QQ by d minus x square. So there is a trick here. What is the trick? And if we break up this as a minus b whole square, a square minus 2ab plus b square. If we break this one as a minus b whole square, and then it becomes more critical. So here is also a kappa, proportionally constant. This is q cancel q and q cancel q. So 1 by x equal to root 2 by d minus x. It is so simple, and the numericals is done. So d minus x is equal to root 2x, and d equal to root 2 plus 1 into x, and the x is d by root 2 plus 1. And if we remove these surds, so we have to multiply it with root 2 minus 1 and root 2 plus 1 and root 2 minus 1, isn't? Yes. So d root 2 minus 1, and this one is 2 minus 1, there is 1. So d root 2 minus 1 is the answer. It is so simple. And the concept is, and the force between this one and this one equal to this one. But if we want to calculate the charge and we equal this repulsion force is equal to this attraction force is equal to this one, then q and q cancel each other. So it is not possible in the way. So this is the answer of the distance. What is the distance? So the distance between this and this one is x. X means d minus. This is the answer. First part. And the second part is, though it may be first or second part. And the second part is, what is the amount of charge? What is the value of this charge? What is the value of this charge in terms of q or 2q? So what is the value of this charge in terms of q and 2q? In terms of q, for that particular case, if we equal these, the attraction force between q and q, so kappa into qq by x square, and this is equal to qq by x square, and this is equal to the repulsion force between these one. So repulsion force between k q into 2q by d square, and then this cancel, and this one also cancel this one. So capital Q by x square equal to 2 small q by d square. So the answer is capital Q equal to 2 small q into x square. X square means this one. So x square means d square into root 2 minus 1 whole square. Root 2 minus 1 whole square. 2 cube d square. 2 cube d square by d square. Oh yes, d square cancel. So 2qx square, that is 2q into root 2 square means 2 minus of 2 root 2 and plus of 1. So 3. So this is 3. Yes, 2q 2 minus 1 means 3 minus 2. So the answer is q 6 minus 4. So this is the answer. So the question is, if q and 2q charges are kept at a particular distance d, where should the third charge be placed so that the total system is in equilibrium? And what is the amount of charge and what is the nature of charge and where it is kept? So the first one answer is, it is kept from a small q charge. You have to mention that from q charge it is kept d into root 2 minus 1. And for the second one, you have to say that the amount of charge, this one must be negative. So the answer for the first part, it is minus of, for the first part, it is answer d root 2 minus 1. And for the second one, it is q into minus of q, 6 minus 4 root 2. Why it is minus q? Because it must be negative, so that this attractional force can balance the repulsion force. Yes, note down, pause the video and note down the methods. So the next one is 28, 29 and 30. 28. So 28 questions is based on different concepts, that is spring constant. And here assumption you have to take. So question number 28. Question number 28. Two identically charged particles are fastened to the two ends of a spring. Yes, spring. So this is a spring. And two charged particles. Suppose there are two charged particles. Here it is a charged particle, and this is q, and this is q. Two spring constant k equal to, and it is given, what is the spring constant? It is the stiffness of the material. So k equal to 100 Newton per meter, 100 Newton per meter. And this charge repel this one with a force, Coulombian repulsion force, and Coulombian repulsion force, and the spring expands. Spring expands, but this expansion is very small. This expansion is very small. Suppose it is x. Suppose it is x. This expansion is very small. Suppose it is x. This is the distance. So the repulsion force will be F equal to kappa into q, that is q square, by what is the separation? Two identically charged particles are fastened to the two ends of a spring of spring constant 100 and natural length is 10 centimeter. So this is 10 centimeter, but this one is 10 plus x centimeter. And if we let x meter is the expansion, x meter, so this is meter is not added with centimeter, so this is 0.1 plus x. So this is 0.1, 0.1. Why it is 0.1, not 0.1? Think about it. So 0.1 plus x. So So 0.1 plus x whole square, F equals to yes. The next one is so the spring and a natural length. The system rests on a smooth horizontal table. Yes, horizontal table. If the charge on each particle is 2.0 into 10 to the power minus 8 coulomb, and the charge is 2.0 into 10 to the power minus 8 coulomb. Minus 8 coulomb. So this one is replaced by 2.0 into 10 to the power minus 8 whole square. F equals to K kappa, that means kappa means proportionality constant 9 into 10 to the power 9. And if the charge on the smooth is this one, find the extension in the length of the spring. Find the extension, that you have to calculate x. Assume that the extension is small as compared to the natural length. So assume that x is very small. Very small means 10 centimeter, very small. It may be 1 centimeter, it may be 0.00001 centimeter. Maybe. It may be. So what is this value? And so yes, let's come to the point. When this particular charged particle expands or repel each other, then the expansion takes place, and this expansion here is given that is it is very small. And if we take the higher power terms in that particular value, there is x, then it is negligible. Suppose you have 1 lakhs and then your father give you a 1 rupee coin, then it is if we compare the particular value with that particular, this is negligible. So this is the concepts or assumption, and question is that what assumption you take for the particular number. So the assumption is when a small value is added with a particular value, and that particular value is very small, negligible compared, and if we take other particular values high power terms, then it is negligible with respect to that particular. So when the expansion takes place, then the force required, the spring force equal to, you know that kx. So k into x is 0.1 plus x. So this is equation 1 and this is equation 2. So this is mainly basically a concept of just spring constant. So first of all, I say that if you completed the numericals from 25 to 30, that it concludes the different concepts that is discussed before. So if you clear this type of concepts, then you can do this easily. So 1 and 2, if we equal this one, k 0.1 plus x equal to k for kappa is a constant. So this is a constant. This is a constant. But this is another constant. This is another constant. It is force constant. It is a proportionality constant. What are the different constants are there? Proportionality constant, it is a force constant, gravitational constants. And why are the different concepts, different coefficients or constant are different kinds? Why? And you have to think about it. So this is equal to 2.0 into 10 to the power minus 8 whole square by 0.1 plus x, and this is the square. It is a typical calculation. The concepts is so easy, but calculation is more difficult. What is the value of k? What is the value of k? K is 100. So we can write here as 100. Yes, this and this one equal. So 0.1 plus x whole cube, and this is equal to 9 into 10 to the power 9 into 2 to the 4 into 10 to the power 16 divided by 100 divided by 100. So 36. So 36 into 10 to the power 10 to the power minus 16 or 2, and 10 to the power 16, 18, 18 minus 9, so 9, 16, or when this is comes to the numerator, then 16 minus 2, 17, 18, 18 minus 9, 18, so 36 into 10 to the minus 9, and so 0.1 and plus x whole cube equal to this one, 36 into 10 to the minus 9. Then we can say that x equal to, this is the answer. So x equal to, think about it, x, we can say that x equal to x equal to, so x is very small, since x is very small, so 0.1 and plus x whole cube means 0.1 whole cube plus 3 into 3 into 0.1 whole square into x plus 3 into 0.1 into x square plus x cube. So all the values here, this is also very negligible since x is very small, and this is also negligible since this is very small, and if we divided this one whole cube, higher power term 0.001 and minus of this one, so this value is too much negligible. So you can write that x equal to 3.6 into 10 to the power minus 8 meter. Why? Think about it. Why? Because all the values here are very small compared, and if we divided this one with that particular value is very small, if we subtract this one with a very small, this is, so division is not matter, this is if we subtract this one with that particular value, so it is a very negligible physical quantity, a negligible value, and so all the values are, you can if we take, so this is the final result, question number 28. Is it clear? So the next question is, 20. The next question is 29. A particle A having a charge 2.0 into 10 to the minus 6 coulomb is held fixed on a horizontal table, and a second charge particle of mass 80 grams stays in equilibrium on the table at a distance of 10 centimeter from the first charge. The coefficient of friction between the table and the second particle is this one. Find the range within which the charge of this second particle may lie. So particle, question number 29, and a charge is held fixed on a horizontal table. A second charge particle of mass, this stays in equilibrium on the table at a distance 10 centimeters. So there is a charge of 2.0 into 10 to the power minus 6 coulomb. and there is another charge. There is another charge. A particle having a charge, this is fixed on a horizontal table. This is fixed. This is fixed on a horizontal table. And a second charge particle of mass 80 gram stays in equilibrium. 80 gram stays in equilibrium. So this is a force mg. This is the force mg. 80 gram. Yes. And the table at a distance 10 centimeter from the first charge. So the distance between this one is 10 centimeter. From the first one, 10 centimeter. The coefficient of friction between the table and this second particle is mu. The second particle is mu equal to 0.5, and the coefficient mu equal to 2. So the frictional force equal to mu into mg, normal reaction. So mu equal to 0.2 into mass is 80 by 100 into g. You have to take it 9.8 or 10, 9.8 or 10. So this Newton is the frictional force. And yes, the coefficient of frictional force is find the range within which the charge of the second particle may lie. Find the range. So this is a frictional force, and this frictional force is equal to the electrostatic force. So electrostatic force is equal to equal to K Q1 Q2 Q1 into Q2. So this is given 2.0 into 10 to the minus 6 into this one. Find the range within which the second charge lies. So F equals to K into this by distance square. So this is the distance, and you have to calculate a particular charge. So this is a simple, that is 10 divided by 100 square, and you can equal this two equations and get the value of Q. So the Q, the answer is given, so you can calculate easily these questions, and the answer is what is the range of this one? So answer is Q equal to plus minus of 8.71 into 10 to the power minus 8 coulomb. What is the range of the charge? And you can take this one as minus to plus this one. So Q square, Q into Q, so Q equals to this one. So if we equilibrate, so each and every, we see that each and every equation, each and every numerical cells, particular two equations is given, and it may be plus, it may be minus charge, because one charge is fixed and the another is, if we range means it is a tricky question and as well as confusing question. It is a tricky question. When suppose this particular charge is negative, so this charge is fixed. It is the main point. Why it is fixed? If this charge attracts this one, then frictional force comes into play. And if this charge repel this one with a particular force, then also the frictional force comes into play. So what is the range? Means just what is the value of the charge. That is, it may be positive, it may be negative. So this one. Okay. Yes, this is in gram. So you have to, gram, so you have to divide it is with 1000, and 10 centimeters, so 10 by 100 square. Yes, this q equal to kappa is 9 into 10 to the power 9, so you have to place here 9 into 10 to the power 9, then equal and calculate q, and this will be plus minus of 8.71 into 10 to the power 6, so simple. Question number 28. Yes, next 20 is done. 20, this is 29, so 30. Next numerical is 30. Next is 30. So a particle A having a charge 2 and is held fixed on a horizontal table. Why it is fixed here? Because this charge can repel this one, so it is fixed at the bottom. So a particle having a charge 2.0 into 10 to the power minus 6, 10 to the power minus 6 coulomb. And so a particle having a charge of 2.0 into 10 to the minus 6 coulomb is held fixed on a horizontal table. Yes, no. A particle having a charge 2 into 10 to the minus 6 coulomb is, and a mass 100 gram is placed at the bottom, and 100 gram mass, 100 gram, and mass equal to 100 gram, and the charge q equal to 2.0 into 10 to the minus 6. So 2.0 into 10 to the minus 6, and a mass of this is placed at the bottom of a smooth inclined plane of inclination 30 degree. So in the inclination is 30 degree. And where should another particle B having the same charge and mass be placed on the inclined? Same identical particles, means mass equal to 100 gram. So 100 gram. Another, where should another particle be having same charge and same mass? So charge is also same, and so that it may be in equilibrium. Yes. So this is the problem. Here a charge of this and mass, this one is fixed, and another charge of mass, this one, on the same charges are placed in the inclined plane. So this is mg. So weight acts along this direction. If we resolute the weight into two components, if we resolute the weight into two components, then this one is theta, so this is mg cos theta, and this is mg sin theta. So this is mg sin theta, and there is a mg sin theta. This is in equilibrium, so mg sin theta can draw this one, but this charge particle given a repulsion force along the line joining the two charges. So the repulsion force is, this is the equation 1. So F equal to kappa into q. So q into q means 2 into 10 to the power minus 6, and this is identical charge, so q square by, and if the separation distance is x here from this one, x, so x square. Isn't clear or not? Two charges are kept at a particular distance x, so F equal to proportionality constant kappa into q1 q2. So these and these charges are equal, q square by x square, and this is equal to this component. So mg, this force, downward force, this is repulsion force, this is along this direction, and this is along this direction. So the answer is mg sin theta is equal to, in equilibrium condition, so 4 into 10 to the power minus 12 by x square, and just put 100 in place of m, so 100 by 1000 gram into g means 9.8, sin 30 degree, sin 30 equal to half, kappa equal to 9 into 10 to the power 9 into 4 into 10 to the power minus 12 by x square, and calculate. and calculate x. Simple. And the answer is 30 27 centimeter from the bottom. So the answer is 27. X equal to 27 centimeter. It is particularly in SI system meter, then multiply with 100. So this is the answer. So the questions number 25 to 30 is completed, and wait for the next day and say wow, what a concept. Thank you.